audible? I'm audible.
Not even reaching to your mind. Also, I increase the reward function to create something. Giving negative reward so that it won't be moving here and there. So that is all.
Hello, am I audible? Okay, so for today's session, we will first go through some questions, MCQ questions similar to the assignments, and then we'll have a demo. We'll mainly look at two main things actually. One will be the different types of ways you can create models in TensorFlow. So the three different types of ways. And the three ways you can define a model in TensorFlow. And the second demo will be just about an introduction of what the accelerated linear algebra library just a small, it will be a very short demo. But you will see that this kind of method offers a much faster computation. Voice is not clear. Is it a problem from my net or there is some background noise? Not sure. Oh yeah, I'm sitting in lab, so there might be some background noise. Okay, I'll try to be a bit more louder. Is this clear? Maybe I can adjust the microphone. Okay, is this clear? Okay, good. So first we'll just go through some questions, MCQ questions, and then we will come to the demos. Can someone check if the link is accessible? usual, we'll just have the questions, and then some time will be given for you to put your answers in the chat box, and after the discussion of this, we'll move on to the next set of questions. So we can go till question 5 when everyone has discussed, at least one answer for each of the questions we have, then we can move to the next question. Okay, I think we'll just discuss the first 5. So, or maybe we'll wait for. Okay, so if we quickly discuss the answers of first 5. So yeah, TensorFlow, you can have any backend, CPU, GPU, TPU, so all of them. Which TensorFlow component is responsible for creating? Okay, so that is B. Both I put B only. tf.data. Then with the default format, so this is actually B, not A. Is actually B. So if you have tried to train some CNN models, the usual way they have data arrangement is that you will first have a number of data points, okay, number of images, let's say, and then store the number of channels. So as you go through the layers of the convolution network, you keep on increasing the number of channels, right? So that the channel number is what is stored in the second form, second thing. Okay, and the height and width. Yeah, 3 is supposed to be B. Then 4 is, yeah, convert to tensor is just a function. And Keras API allows you for fast and easy prototyping, so B works. I mean, the reason the Keras API is good is because it doesn't require you to write the model from scratch. So there will be already layers defined for, let's say, dense layers, max pooling, convolution layers, different types, 1D, 2D, all of that. So in that sense, it's actually making you the prototype faster. So now we'll move on to the next set of questions. Okay, you can fit 5 of them in this. 5 is B, yes. guess we have answers for all 5, rather all 6. So which TensorFlow feature? So B answer is B. Yeah, tensor TF dot function. And then what is the mixed precision training? Yeah, so mixed precision is basically used for reducing the memory and speeding up your training process. So 7C. Then 8 is TensorFlow 2. TensorBoard, as we saw last time, and we have used in PyTorch also. So 8 is A. Auto tune, so it cannot optimally choose the number of parallel calls without you having to explicitly set them up. So it will that's the, as the name says, it's auto tune. So 9 is B. And then 10 to the function negative impact on performance. Inconsistent input shapes. In fact, your model itself won't run at all. Then what is the primary use of TensorFlow's mirror strategy? Yeah, 10 is A. So C. Correct. It is C. So we'll move on to the next set of questions. Okay, so starting from 12th. The TF dot distribute strategies for perform distributed training. TensorFlow strategy would be suitable most for training on multiple GPUs. So 13 is B. Okay. Multiple worker setting. Then yeah, 14 is C. 15 is the functional API. 16 functional over sequential is so functional allows for a more complex and nonlinear topologies, whereas sequential allows for a more step. 15 is what? 15 is functional API B. Then 16 is B. And 17 sequential model, yeah, is again B. So just to summarize, 12 was A, 13 was B, 14 was C, 15 was B, 16 was B, and 17 was also B. Okay. And this last three. Yeah, so as the there's name is like input layer is for defining the input shape and batch size. Then insert's rank is the number of dimensions of that insert. So 18 is basically B, 19 is so B, and 20 is yeah. So this D. So different. All of these three offer better model deployment on different types of platforms. So for edge devices, for example, TensorFlow Lite is commonly used, and for hosting and all, and so for serving GS. Okay. We'll wrap up the questions part and move on to the demo session. So right now we will just quickly go through a demo of showing how you can define the models in TensorFlow. So TensorFlow allows you to, through this Keras API, it allows you to define models using either the sequential API or the functional API. Or the subclassing method. And this one is very similar to the PyTorch way of doing things, which we saw in the last live session. For PyTorch, when we defined the model, we did it similar to this subclassing method. So just quickly I'll share a collab book link. Just check and let me know if that is. So you won't be having an edit access to this notebook, but when you click on this, you can basically at the top you will have an option of save to drive, and you can click on that and make a copy of this, or rather copy to drive, and you can copy the notebook to your drive and run it. I hope my screen is visible. And I hope the notebook is also accessible. Right? It says unable to copy. Is that so? Because I have given viewer access to everyone with the link. Oh, you have out of drive space. Maybe you can open it in some other Google Drive. Someone raised a hand. Do you have any doubt? Okay, either way, you have the link, you can open it later also. Just copy and keep it somewhere. For the time being, we'll go through the code. We'll just briefly look at what is the key differences between the three types and discuss some advantages of using each of them. So the dataset that we are looking at today is this spoken digit dataset. So for that, like passing that, you need this PyDub library, which we are just installing in the first cell here. The thing is, this spoken digit is very similar to your MNIST, which is with images. So this is an dataset of audio files basically, with people saying the name of a digit, and the model is trying to classify what digit is spoken. Okay, and the audio signal, we are going to assume that it's like a wave basically. So it's a 1D signal, 1D wave basically, and we are going to use a 1D convolution to run over the signal, and we are going to pass it through layers of convolutions, and then use a dense layer, and finally make the classification among the 10 digits. That is the model that we want to actually look at. But before we go ahead and do that, you can just load the dataset and see what is the content. So the dataset has 10 classes, 0 to 9, and the audio signal in the sampling rate of the data in all these audio files is about 8,000. and this is just a function for pre-processing the data. So mainly we are making all of them same size and padding them if required, and we are normalizing them, the audio, so that when we process it, it doesn't cause any problems. So the model should this is a common practice to do on the dataset, and along with the so we are returning out from this process audio function the audio the signal itself and the label of it, and then we are doing the mapping. So we are going to apply this pre-processing step on our data, and this will pass all your data set and pre-process it according to this function, and at the same time we are passing this num parallel calls. So this will automatically optimize the way when we are loading the data set, it will optimize the way data is accessed. And so number of examples, train size, validation size. So 80% of data we are keeping for training, 20% for testing, for validation. And yeah, so batch size is 32, and we are using this prefetch argument. So prefetching is to allow instead of going for a sequential approach for CPU GPU computations, so you take the data for one batch, then process it through the GPU, update the weights and so on, and then only you sample the data for the next batch. Instead of doing that, if you want to parallelly run the workload on CPU as well as GPU. So while the data is being passed through this pre-processing step, you can keep on updating the weights on GPU, and while the GPU weights are being updated, simultaneously for the next batch you can keep on parsing the data. Okay, and at what rate this process should happen is we are basically automating that process. So we are using the auto tune method, and the model that so we look at the three ways we can create the model. So first is the simplest way, which is the sequential API. So in this we are trying to use this model for which the input shape and which we predefined. So it was a fixed shape that we were looking at for all the audio samples, and so in the sequential API you can basically see that it's the output of one layer. This kind of API is used to define models which are having more of a linear structure. Something, your input goes in, it passes through one layer, then it passes through another layer which you have defined next, then next, and so on. But so there are some limitations to this approach, but for this exercise, this API is sufficient for us to create a model. So as I said, we are going to use a 1D convolution to pass over the entire wave data, and then we are going to pool the thing, and so it basically halves the amount of data. Then you again use a 1D convolution, again use max pooling, again go through convolution, then you average the entire thing. You have finally 128 neurons in a dense layer, and that goes down to finally only 10 classes, and you are using a softmax, so you get a probability of basically a particular audio signal being in each of the class, and that is your return. So you are getting an vector output of 10 numbers, all in the range 0 to 1. So that is what we are doing here. And this is our sequential model. And unlike in PyTorch, you don't just run the model directly. You first compile it in TensorFlow. So that we do here. We are defining our loss as per the categorical class entropy, which is the most common way of defining the loss function in case of classification problems. And we are basically looking at the accuracy as a metric. And if you run here, so for now, for this demo, I am just keeping the epochs as 3 so that it runs fast quickly. You can train it for more number of epochs and see how the loss evolves. And you will see that the training process is going quite slow because I have actually kept it on CPU right now. So the runtime type is actually CPU. We'll later see along with GPU how this works. So the auto tune functionality is not basically utilized right now. Because there is only CPU. The machine, the runtime that we are accessing from Colab is just CPU. But you can try it with GPU. I think it will run faster for you. Till this point, if you have any doubts, you can ask. This is how function auto tune works, both CPU and GPU. So I mean it can't optimize if you don't have different workloads. If the entire processing is happening only on CPU, it has to happen sequentially. So you are not training the model on GPU and parsing the data on CPU. That way is not happening. So right now the auto tune is not really working, doing its thing. I mean, we have set it for prefetching, so that is not being utilized right now. If you want, you can just change the runtime type here and run it. I'm not sure whether I will be able to, but maybe I can try. Just give it current session. Oh, fine. Let it run. In the meantime, maybe I can go through the next parts of the code. So I ran it before, so over 10 epochs it was the loss, the accuracy was going over 58%, and you can increase it if you need. This is the validation loss, basically, validation accuracy and loss. So the 20% of data which was not being utilized, that we are computing this loss and accuracy. Okay. Now going forward to the functional API. So in this case, we are actually, there's more freedom to have a more complex nature of model. So you can have, as you can see here, you are basically defining layers, these inputs, and then these inputs are going as arguments to the next layer, and you are creating some new output which itself is going as input to the next layer, and so on. So this kind of method allows you to have a more, so basically if I had set these variables with the different names, I can pick let's say the output of this particular layer, and I can send it to a completely parallel network which is independent of this. So instead of sending, in fact, along with sending this way, if I want to send it through another network, and maybe at the end of the process I want to, let's say, combine the output of two different networks and use something like an ensemble model, I can do that with this API. So maybe let's say I call this one as x1 and go forward through this code here through that x1, using that x1, and I can have a parallelly a different set of lines which are defining which are starting from this x1 and going through a, let's say, different number of features along the way, or different number of filters, and that also can be done. So you can combine parallel models in a single class, or rather in a single function. So that is one of the advantages of functional API. Is that part making sense? If you have any doubts, you can ask. Here also we are in fact following the same procedure for training. Only the way the model is defined is different, but in fact the model is exactly the same. We are just defining it in a different form. It was confusing. Can you repeat once again? Okay, I'll just do one thing. I will switch to the tablet and maybe I will show it there. Just give me a minute. So the thing that I was actually describing was that in case of let's say the functional API, we'll just look at the model. If you can check on the screen, on your collab screen, what the model was like. So it basically had an input layer which was defined using the input Keras input functionality, and input shape was given. Okay, let's say I want to take this input through two different channels. Okay, so I have network 1, I will call this CNN1, and I have another network, let's say, and maybe at the end of this network I have a softmax which is predicting the probabilities, the 10 probabilities of a particular audio signal being one of the numbers, and at the end of this also I have another set of 10 probabilities. Let's say I wanted to create such an architecture and at the end maybe I'm going to take a majority vote. So if uh, if this model is more confident on its output, or let's say in fact not even two, we could have multiple, we could have CNN3 also, and this is also returning at the end a set of 10 probabilities, and you could go for an majority vote. So let's say this through this pathway you are predicting the output is 3. Let's say from this you are predicting it as 2, and this is also predicting as 3. So maybe you want to take a majority vote and consider the probabilities given by all 3 of these models and use that as the prediction. So this kind of method is possible when you use functional API. So I'll just describe what I was saying when I was looking at the code. So in the first line you basically had the input defined, and this input went through a convolution layer, let's say convolution 1D layer, and the input went through it, and you got some output X. Okay, so this con 1D layer that you had was basically, it was using 32 filters of kernel size 3, let's say. So instead of that, I could have the same input layer going in the convolution CNN2, maybe that 1D convolution layer. Maybe I can have a different number of kernels, let's say 16 filters, and I can probably use a different filter size also. Let's say I use filter size of 2, and that will give me out some. So I'm calling the output of the first one X1, the second one X2. So as you can see here, the output of the same input, when it went through the convolution layer, it created basically 2 different outputs, and those 2 different outputs can then go through a different pathway. Okay, is that making sense? Okay, and so ahead of this X1, since the size of this X1 and X2 they might be different, I can keep on going through a different pathway, and I can ultimately, finally I'm going to go over dense layers and finally we are going to get out the 10 probabilities only, but the model themselves might be different. Okay, so instead of going the entire way through a CNN, I can just at this point itself, that audio signal, maybe I can probably use an LSTM. So one of them can even be an LSTM network. There's no restriction that it has to be a CNN. So you can have multiple possible ways in which this architecture can be defined. So there is no restriction for it. So the functional API kind of allows you to do something like this. Unlike this, if you had using the sequential API, you can't do such a framework, because once you have defined the layers, you are just defining the architecture. You are directly defining the architecture itself. You are not taking the inputs at every step and passing them in different forms. That is not what sequential API allows you to do, but functional API allows you to do that. Okay. Since you have taken different layers, which output will be considered as final output? Okay, so the thing is, in this particular case, I might look at the probabilities of So I'm just this is just a dummy example, but I'm not going to such an architecture. In such a case, you won't be like preferring one uh, output over the other. Maybe, yeah, no, in fact all of them will give some result. So this output one, all of them are giving some result. The way we would get the final result from the model could be based on, let's say, the average of the probabilities for each of them, something like that. And you again have to probably normalize it, something like that. You can use different methods, but it's more like a majority vote kind of architecture. So from each of the different pathways, if you are getting a good result, or some of them are not giving good results for a set of inputs, but they are giving good results for a set of other inputs. So in that case, you can have like a majority vote kind of architecture, and you can work with that also. So it's like a more like a combination of what output you are getting from each to use as the final output. Okay. So I'll just switch back to the subclassing view. So this also you can just run for different number of epochs. The architecture is exactly the same, so the results are probably not going to be that different, but you can test that out. In the subclassing method, so this is more like even you can do much more in subclassing method than what you were doing for in the functional API. What you are doing, you can do even more with subclassing methods. In this case, you are having in fact sort of like a dynamic layers. So over the course of your model training probably, or in fact you can even have something like if loops, or so here you are actually defining the entire forward function on your own. So on by look, this might look very similar to the functional API. So here also you are sending inputs to something X, and then that X is going through pooling, and then the X is going through another convolution, pooling, so on. It might look on the appearance, it might look similar, but this is, you can imagine that this itself is a function of a class, and depending on some like class variables, you can have some dynamically varying forward function. So here in the call function that is defined here, you can actually have something like if loops. So if, let's say, a particular parameter is changing to a certain type, so let's say during the course of your model training, you look at certain weights on a particular layer, and you see that, let's say, they are getting biased, for example. You can adjust the model in certain way, and you can have a if loop condition present inside this. Okay, so some funny things like that can also be done through this API. Okay, is that making sense? So the entire forward function is in your control, basically. That's what I'm. In fact, you can go with even, so let's say a particular output of a layer, you want to pass it through, or you can just want to adjust the output of a particular layer and do something with it. So that also can be done with this. Let's say you want to, I don't know, maybe shuffle the output in some way, but it's not a good idea actually to do that, such a thing. But I'm just saying that this method can gives you the freedom to do that. You won't be actually doing it, but if loops and so such things can be incorporated in this, because it's more like a Python function. So we are just putting it, the entire forward function is in your, and the training process for that is also defined here. And here it's exactly the same model which we are doing, so the result might not come out different. Some slight variations might be there, but that's it. Okay, so that's all I wanted to cover for this part of the demo. And if you have any doubts, you can ask. Else we can switch to the next demo. In fact, I just tried to connect to the GPU instance here. Just check whether it is still available. In the meantime, you can ask questions if you want. Okay, so it did connect to our GPU instance. So we are just checking number of available GPUs, and so we are connected to a GPU instance. We have GPU available. Nothing here is actually different from the previous code. It's the exact same code actually. But you will see that this will run much faster because basically it's running on GPU, and as well as the auto tune is in place. Def con def forward same. Yeah, so in PyTorch the subclassing method is like the commonly used method, and then basically instead of this call function we call it the forward function, whereas in TensorFlow it's called the call function. You can see this is running much faster than the previous one. So yeah, so this GPU method is kind of running faster. The rest of the code is exactly the same. We'll quickly go over the XLA. I will just share this collab link. You can check whether that notebook is accessible. Yeah, so we'll just look at this XLA functionality. So XLA, as you know, stands for accelerated linear algebra. So in most of the deep learning applications is just a bunch of matrix multiplication or matrix vector multiplication. In fact, all our standard neural networks, even convolutions, can be written as a simple matrix vector multiplication form. And so in this demo we are actually seeing basically this is still I'm going to run it on CPU. So what is the advantage of using this XLA method, or rather the JIT compilation? So just JIT stands for just in time. And so in TensorFlow you can basically set this JIT value as either false or true, and it will compile it beforehand or not to the C++ backend. That is what is decided based on this value. So we are just trying to do a simple matrix multiplication here. Okay, so we have a matrix A which is of size 1000 cross 1000. So it has 10 power 6 elements, and a matrix B which has also 1000 cross 1000 size. Okay, so it's a pretty big matrix. Okay, it has 1 million elements. Both have about 1 million elements. So this kind of a multiplication is huge. And so we will see basically the difference between time with and without use of this JIT compilation. And you can just run the code. So you can see that on a CPU the order of magnitude of difference is about almost 3 times, right? So even on a CPU, changing the so your Python defined operation, you can let it compile beforehand and let it go through the C++ backend, so on, C backend, and it can execute the same function much faster. Even on a CPU you are able to get a 3 times three times faster computations. And in the GPU notebook also I tried to run it. So it's the same code, again 1000 cross 1000 matrices A and B, and we are trying to multiply those. You'll see that in GPU mode it's actually much more effective. So on a normal GPU without the JIT compilation, you are still having much improved performance. So compare that with the, so on a CPU it was 0.07 seconds. This is now in 0.01. So here itself you are having about 6 times improvement. Okay. From CPU JIT to normal GPU, but with the use of JIT on GPU, you are having an even more performance boost. So it's almost order of 10 difference between GPU computations with and without JIT. So that is what I wanted to show. So there is a potential for improvement of your functions a lot, but as we know, like as you have seen in the lectures also, not all of the functions can be compiled through this JIT method. You have to, some of them can be improved, some of them may not improve. So that depends. So you have to first check whether it is compilable through JIT. It will give an error if it's not possible. And that's it. I have these demos for today. If you have any doubts, maybe we can cover those. Else we can wrap up the session for today. Does anyone have any doubts in any of the demos or questions? script which can be pre-compiled using JIT compilation. Yeah, I mean, if it can be pre-compiled. What is going to happen is the code is basically going to get compiled in a language which is closer to the machine code, and that will increase the computation speeds basically. So unlike Python, where let's say Python has to be interpreted right all the way. So instead of that, this machine code can probably run faster. So you can, whichever can be compiled, you can basically run that part of the code faster. That you can do. Since you mentioned JIT compilation using TensorFlow only. No, I mean, it's not like you can use JIT only with TensorFlow. There is something called the JAX, which is basically you can convert your PyTorch code to also have this JIT functionality. So it's not necessary that your code has to be written in TensorFlow only. So JAXPy is the library which you can use to convert your PyTorch code and also run it to JIT. So it's an alternative, you can say. So JAXPy is more like a substitute for NumPy. Okay. So in case if nobody has any doubts, we can close the session, or if you have, I will wait for another 5 minutes maybe. Was everyone able to run the codes that we discussed today? Okay, among the APIs we discussed for model definition. Okay, so I mean, in general, it depends on your application, but both functional API and subclassing method, they are both good enough, and you can define most of your models with either of the methods. But if you want to dynamically change, let's say, the forward function itself, that can only be done through the subclassing method, and subclassing method pretty much allows you to do quite almost all of the stuff that functional API also allows you to do. but functional API is also good enough. I mean, the architecture wise it's also quite simple. So, but in case of let's say you want to define a completely new type of layer, let's say in the network, I think that might be more possible. In fact, that can be done with either of the methods. uh, in case of subclassing method, you will have to define it more rigorously. You have to write the entire of it. In functional API, you can just convert a Python function that you wrote to that tf function, maybe, and then you can pass that in the flow of the model. But in general, both subclassing and functional API are good enough. Complex fluid dynamics problem. So, for let's say applications related to pins such as physics informed neural networks, pretty much subclassing method is good enough for it. I mean, you can define the exact same way you are defining the function in, let's say, PyTorch. You can use that same type of writing of the model description. You can use it in TensorFlow as well. So, in that sense, subclassing method would be a good option. You can do the same thing with functional API, but I think I'm not completely sure, but you can check. But I think subclassing is sufficient. And for if the most research applications in research papers, they will define a novel way of defining a neural network or the model. So in that case, you would want to use or you would want to write the code which is exactly replicating that. So in that scenario, you can go with the subclassing method. You have full control of the forward function. So that's what I would suggest. Okay. So in case if there are no more doubts, we can wrap up the session. Okay. Okay. Yeah. Thanks for attending the session. Yeah. So we'll close the meeting.